So when we are talking about the sum of an infinite series, in my previous video, I talked about whether the limit exists or does not exist. We want to give it a bit more precise mathematical terms. So in particular, if the partial sum s of n, as n approach infinity, if it exists, if it's a finite number, then we call that a convergent series. On the other hand, if the limit does not exist, then we call that a divergent series. Okay, and we saw an example earlier, right? A geometric series that has a common multiplier or common factor of 1/2. When r is equal to 1/2, it actually converges. A divergent series example would be the arithmetic series that we did, and let's say it's 1 plus 3 plus 5 plus 7 plus 9 plus ... If it's an infinite number of terms, obviously it's going to get larger and larger, and it just approaches infinity. Well, the natural question would be, how can we determine if an infinite series converges or not? So let's take a look at a couple of examples. Let's look at the previous example, sigma k equal to 1 to infinity, and each term is defined by 2 plus k. So obviously the first term when k equal to 1 is going to be 3, and then this is going to be 4, this is 5, 6, 7. I know we're adding them together. What is the nth term? Well, it's going to be 2 plus n, right? When k is equal to n. What about the term itself? Okay. Before we look at the partial sum, let's just look at the term itself. Does 2 plus n goes to infinity as n approaches infinity? Yeah, absolutely. So when the term itself increases without bound, then for sure the sum would have to increase without bound, right? You're adding a term that gets larger and larger. So therefore, the sum of the series cannot converge. So that is an easy conclusion. Now what about the previous example of a geometric series? Go to n. Again, I have 3 times 1/2 to the power of k minus 1. And the first term is 3. The second term is 3 times 1/2. The third term is 3 times 1/2 square, so on and so forth. And this is 3 times 1/2 to the power n minus 1. You notice that as n approach infinity, the term itself approach 0. As n goes to infinity. Okay? So that means as n gets very large, what you're adding to the partial sum becomes less and less. And in fact, it becomes so insignificant that it doesn't really change the sum as n approaches infinity. So that is clearly one criteria for the series to converge, is that is as the nth term approach 0 when n approaches infinity. Okay, so that is clearly a necessary condition. But is it sufficient? If the nth term approaches 0 when n becomes large, is that enough to guarantee that the series converge? Let's take a look at another example. So to answer that question, let's take a look at a series called the harmonic series. And it is almost like the reciprocal function. The way it works is that is a term comprised of 1 over k, where k is the index of the term. So when k is equal to 1, I have 1 divided by 1, which is 1. And when k is equal to 2, is 1 divided by 2, that's 1/2. When k is equal to 3, is 1/3. When k is equal to 4, is 1/4 plus 1/5. And for the nth term is 1 over n. And as we see, when n approaches infinity, 1 over n approaches 0, right? So therefore, in this case, the nth term indeed approach 0. But does that mean the partial sum exists? Okay, as n goes to infinity. Okay, we have to look at it a little bit more in detail, and let me explain to you how it's done. And since there's no formula, we haven't learned any formula about how to calculate the partial sum for the harmonic series. Okay, so we're going to do a little algebraic trick and see if we can get some insight into whether this series converge or not. Okay, so I'm going to replicate the series on both sides. On the right hand side, I call the right side series. On the left hand side, I call it the left side series. Okay, and the right hand side is the original harmonic series, which is 1 plus 1/2 plus 1/3 and so forth. Okay, and I'm going to do the same thing on the left hand side. So I'm going to write 1 plus 1/2 plus 1/3 so far. Okay, so as you can see, the right hand series is the same. The right side series is equal value to the left side series up to this point. Then I'm going to continue adding one more term to the right side. Okay, now on the left side, I am going to also add the next term, which is 1/4, but I'm going to replace the previous term of 1/3 by 1/4. Okay, and you'll see why in a minute. So now the right side is got to be larger than the left side, right? Because 1/3 is bigger than 1/4, and all the other terms are the same. So I can no longer say they're equal, but instead the right side is now larger than the left side. Let me examine what is the sum up to this point on the left side. So I have 1, I have 1/2, and I have 1/4 plus 1/4. And that is the same as 1/2, right? So far I have 1/2 plus 1/2 plus 1. So the partial sum up to this point is 2. Well, let me continue adding more terms. So on the right side, I'm going to add 1/5 plus 1/6 plus 1/7 plus 1/8. Okay. On the left series, I do something similar, but instead of adding 1/5, 1/6, 1/7, 1/8, I'm just going to add 1/8 4 times. Plus 1/8 plus 1/8. Okay? Same number of terms, but the values of the terms are different. Well, as you can see, 1/5 is greater than 1/8, 1/6 is greater than 1/8, 1/7 is greater than 1/8. So therefore, the right side series is still greater than the left side series. In fact, it's greater than before. Well, let's see if I can add up these 4 terms of 1/8. That's going to be 4/8, which is equal to 1/2. Okay, so if I rewrite these all in red, so the first term is 1 plus 1/2 plus 1/2, which is made up of 2 terms of 1/4, plus another 1/2, which is made up of 4 terms of 1/8. Okay? Now, you can imagine I can keep doing this. Now I have 1/9 plus 1/10 plus 1/11 plus 1/12 plus 1/13 plus 1/14 plus 1/15 plus 1/16. Okay, I have 8 terms, and I'm going to do the same trick like I did earlier. I'm going to add 1/16, 8 terms of those. Okay? And again, the right side series is still larger than the left side series. And if I add those 8 terms of 1/16 together, this is going to be equal to 8/16, which is again equal to 1/2. So you can imagine if I keep doing the same thing on the left side, let's say the next time I'm going to add 1/32 plus, but I'm going to add 1/32, in this case 16 terms, I'm going to end up with another 1/2, right? So the left side series is basically 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2. And because it's an infinite series, I can collect as many terms as I want. I can have as many 1/2 as I want. So does this series converge? Absolutely not, right? Because if you keep adding 1/2, it just keeps increasing larger and larger. And if the right side series is greater than the left side series, then the right side series cannot converge, because the left side series cannot converge, and something that is greater than it for sure cannot converge. So therefore this does not converge. Okay, so the reason why I brought this up is just the fact that when you have the nth term approach 0 as n approach infinity, that is in and of itself not sufficient to guarantee convergence. The only way to guarantee convergence is if you can calculate the partial sum, and if you take the limit of the partial sum as n approach infinity and it converges to a finite number, and if you're successful in doing that, then you can conclude that it indeed converges. Okay? Now, because we didn't give you the formula for the sum of harmonic series, in fact, there's no formula for it. It's a very complex mathematical trick to make it approximate to actually the logarithmic function. But you do have the formula for a geometric series, and you do have a formula for the arithmetic series, and you can use this test to see whether the geometric series converges or not, and similarly whether the arithmetic series converge or not. And as we talked about earlier, because arithmetic series just keep adding a larger and larger number, or a more and more negative number, as the case might be, therefore arithmetic series generally do not converge. And geometric series will converge subject to certain conditions when r is less than 1. Okay? And you will see that in the problem set.